In 2005, the year of Katrina, the National Hurricane Center exhausted its pre-season list of 21 names for Atlantic storms. This rise in frequency and intensity sparked international fears that a supercycle of hurricanes will soon strike another major city, this time in unexpected places further up the coast. So scientists like Dr. Henry Grissino-Mayer were given a challenge to find evidence of ancient hurricanes, reveal their cycles, and see if they resemble the pattern that threatens us today.
So now what we're using, the tree ring record, is to learn about past hurricanes by actually picking apart the tree rings on a much finer scale to learn about past hurricanes, not only for the 20th century, but for many centuries.
Oftentimes at the top of these hurricane deposits, he finds a thin layer of charcoal.
Much like forensic scientists, we actually use patterns in the tree rings, just like fingerprint patterns. We use the patterns in the tree rings from the living trees, and we overlap that pattern with the pattern of tree rings from the dead trees. And that's how we're able to assign years to the tree rings from these deadened down pieces of wood.
It starts with Grissino-Mayer's favorite, the longleaf pine, a native tree that once made up the lush coastal forests of the Carolinas, until the demand for ship masts and turpentine decimated their numbers. This tree is hurricane-proof and outlives many of its neighbors. Its wide root mat quickly draws up water, which it incorporates into its growth layer, manufacturing cellulose in the process. The composition of the oxygen in the water that makes up hurricane rainfall is distinct.
So they essentially are drinking hurricane juice, if you will, and incorporating the water from the hurricane. The oxygen in the water from the hurricane is used when the tree makes cellulose.
Within that cellulose lies the hurricane signature in the form of oxygen isotopes, the chemical signature Grissino-Mayer is looking for. Claudia Mora merges disciplines with Grissino-Mayer to get at the hurricane story embedded in the wood.
We're working on the late wood here, and what we're trying to do is peel this off.
So we're just trying to find that cellulose that's being made from the water drawn up and retains that hurricane signal. Because oxygen is in just about everything, it's really just a tool for a clever chemist to use.
Grissino-Mayer shaves a cataloged ring. Mora chemically extracts the cellulose. Packing it into a tiny ball, she fires it through a mass spectrometer. It separates two distinct types of oxygen isotope, one weighing more than the other, atomic weights of 16 and 18. The composition of lighter and heavier isotopes in hurricane rainfall differs from normal precipitation. A hurricane relies on repeated condensation for energy. Water vapor rises, condenses, and forms a cloud droplet. This droplet falls as rain, and it takes with it more of the heavier isotope. It leaves behind more of the lighter isotopes, which still circulate in a vapor state.
If you take a rain cloud and you wring it a little bit, there goes some of the precipitation. You get a lot of the 18O falls out. You wring it a little bit more, well, you still get more 18 out than 16, but the relative amount has changed a little bit. There's just not as much 18O left. By the time it hits the land, it's very different than normal precipitation.
After a year and a half processing and recording centuries of tree rings,
the day we figured out that it worked, it was Miller time.
A season-by-season record of hurricane cycles that date back 4 centuries reveals ancient on-again, off-again patterns. It confirms that our current active cycle may not be an anomaly. The East has been battered again and again by hurricane cycles that may have lasted decades at a time.